All right. I think this will work. So can you see my main window here with the aldec window visible?
Yes.
Cool.
Yeah,
All right, and I can switch tabs, so we're going to see if this works. Um, all right, let's make a new project. So I'm going to close this window out. So I'm just going to close workspace, and it's going to ask me about this will stop the simulation. That's okay. Um, Waveform has been modified. Do you wish to save it? I'm going to say no. So that closes everything out. So this is kind of my starting place, right, where it's just saying workspace not loaded. So let's make an adder. So I'm going to say file new workspace, and I'm going to call this add test. I'm going to create an empty design. I'm going to switch to Verilog. I'm going to call it add test. And I'll go ahead and say finish. And then I'm going to right click and say new Verilog source. And I'll say next. I'll call it add test. And now we're going to define the ports. So let me see if I have my camera still set up. I don't think I do, so let me set up my camera. That's a big camera.
they look normal with me.
Yeah, but I'm on a 55-inch monitor and it's like filling the whole screen. So it's like, it's the clipboard that ate Cincinnati.
At 4K, I'm assuming.
Yeah.
Very nice.
Yeah, so I normally have like my laptop, which is like, 1920 by 1080, and that's what you're seeing, and that's what gets recorded. And then I have the big monitor on the side to, to follow the chat window and things like that. All right, so let's make a 2-bit adder. We've done this a number of times already. So let's redraw the system diagram. These are going to be 2-bit inputs. I'm going to call this A and B. We're going to generate a sum. And how many bits is the sum going to want to be?
3 bits.
3 bits will work. So 2-bit number, the largest we can do is 1, 1, which is 3. 3 plus 3 is 6, which is less than 8. So we can get away with 3 bits. We could do it with 4 bits, and we just have, our most significant bit always being a 0. So let's make a 2-bit adder. So I'm going to use the system diagram to inform what I say here. So let's start off with new. I'm going to make a port called A. It's going to be an input port, but we're going to make these arrays. So if you've done programming in C, Python, etc., you know about arrays. An array is like a regular variable, but it can hold more than one number. So we're going to have an array of bits. We're going to want to hold 2 numbers. And usually we think of this as, A1 and A0. And so over here where it says array indexes, I'm going to set this first index to 1, the second one to 0. So this is A bracket 1 colon 0, which means there's 2 bits, bit 1 and bit 0, and A1 is the most significant bit. So that's a 2-bit input. And I'm going to say new, and I'm going to set up B to be another input, and same thing, I'll set this first index to be a 1. So that's my 2 inputs, and then my output I'm going to call sum, and I'm going to make that a 3-bit thing, so it'll be sum bracket 2 to 0. And this business of counting from 0 on up is something that is usually pretty weird when you first encounter it, and eventually it's the whole way you think of the world. You think everything starts at 0. So this is 3 bits, even though it starts at 2, it's actually bit 2, bit 1, bit 0, 3 bits total. All right, so we'll say finish. There's our Verilog code. I'm hitting Control S periodically just to kind of save my code along the way in case this thing crashes. So what's changed here? Well, really what changed is in the input statement where it says input A, there's these subscripts in front. So it says A is now an array of 2 bits going from bit 1 down to bit 0. Sum is 3 bits going from bit 2 down to bit 0. All right, how do I make an adder?
Oh, quick note. Did you want to put the sum in the input or as an output?
I wanted it to be an output. Did I mess up?
Yeah, you put it as an input.
My bad. Oh, and I just encountered a serious error. Okay, maybe that was the error. All right, well, thank you for catching that. And let me go ahead and restart this. All right, one sec. All right, so let's go with file. Recent workspaces, add test. There we go. All right, so let's change this to an output. And that wizard that we use when we first start this, where we create the system diagram, is really just a front end to write all of this code for us. We don't have to use it. We could, in fact, say create an empty design and just type this code in by hand, but it's a shortcut. So if I mess up, I can just change sum to be an output. All right, so now let's go ahead and make an adder, and I'm going to get rid of these statements here. And I'm going to indent some stuff. So if you highlight and you hit tab, it'll indent. And that's all you got to do to define an adder. The compiler understands that plus means addition, and it will design a circuit that takes these two 2-bit numbers and adds them together. And yeah.
So what if, like, I guess, can you do something for, like, just, like, the first index of A? Like
Yeah.
A1?
You could do A bracket 0 or A bracket 1 or things like that.
Okay, so you could just do brackets like
Yeah.
C and
Yeah, just like in C. So this is part of the magic of Verilog, right? You know that if you want to design a 2-bit adder, you've got to, make a full adder, half adder, truth tables, K-maps, XORs, ANDs, things like that, put it all together, right? In Verilog, I can just say sum equals A plus B, and it will do all of that for me, right? It figures that out. And if I come here and I say compile,
You don't even have to add the individual bits. It's just going to add both of them.
it's just going to add them together. But I forgot to say assign. So if you get an error, you'll get a message down here saying error. It'll put you a red squiggly line saying where it is. And if you hover over that, it will give you some more information. So I forgot to say assign, so I'll put that in. I'll right click, I'll compile, and now it says 0 errors, 0 warnings. So let's see if this actually works. So let's come over to File, and we'll do New Waveform. And I'll come over to Simulation, Initialize Simulation. It'll ask for the top level module. I'll expand this, pick on my module name with the gold star next to it, say Apply and OK. And now I'm just going to Control A to select all three of these and drag them in here. And there's a little plus sign next to these. I can expand this and I can see A1 and A0. I can expand this and see B1, B0. I can expand this and see the 3 bits of sum. So I'm going to leave those unexpanded for now. And I'm going to select both of those, right-click, and say Stimulators. So in this case, for A, I'm going to use a counter. And I'm going to start from 0, modify by 1 every 100 nanoseconds, and I'm going to count up. And I'm going to say Apply. So A is going to start from 0. It's 2 bits. It's going to count every 100 nanoseconds from 0 to 1 to 2 to 3. That's going to be 400 nanoseconds before it gets back to 0. So for B, I'm going to set up B to be a counter, but I'm going to make that count more slowly. I'm going to have that count every 400 nanoseconds. And I'm going to say Apply. So now the setup is like this. Right, A is counting. It's going to start off at a 0, and then it's going to count to a 1, and then a 2, and then a 3, and then back to 0, 1, 2, and so on. And since to test my circuit, I want all combinations of A and B, I'm going to let A start as a 0, and then I'm going to change to, this is why I use pencil, start off as a 0, and then I'm going to change to a 1 when A has gone back to a 0. And then I'll change to a 2 when A goes back to a 0. So I'll get these different combinations. So this you just kind of figure out by trial and error. But basically, I'm setting up 2 waveforms that'll give me interesting combinations of A and B. So let me apply that and close this and come back in here. And let's just go ahead and start simulating. And I'm just going to click through a whole bunch. And then I'm going to Control scroll wheel to zoom out. And I'm going to Shift scroll wheel to scroll. And you can see what's happening here, right? A is changing from 0, 1, 2, 3, 0, 1, 2, 3. It's looping. And each time it goes back to a 0, B is incrementing. And some
hexagons like that. Mine's just like solid bars, but if I scroll over it, I can see the values change.
Yeah, so Control scroll wheel to zoom in or out.
Oh, I see now.
And once you zoom, where you are on this changes. So sometimes you need to either grab this and move back to the left, or Shift scroll wheel to pan. So this is a pretty clear demonstration, right? If A is equal to 1 and B is equal to 1, the sum's equal to 2. And if I click right here, right, my cursor is at, 542 nanoseconds, and I can see A is 1, B is 1, sum is 2. Here's 2 plus 2 is 4. Here's 2 plus 3 is equal to 5, or 3 plus 2 is equal to 5. And if I expand these, you can see the waveforms that we're used to seeing, where, at this point right here, A bracket 1 is a 1, A bracket 0 is a 1, so that's the number 3, 1, 1 in binary. The number B bracket 1 is a 1, B bracket 0 is a 0, that's the binary number 1, 0, which is the decimal number 2. And 3 plus 2 should give us the decimal number 5, which in binary is a 1 and a 0 and a 1. And there's a beautiful timing diagram for a 2-bit adder. All right, let's go back to our add test circuit. Let's make a subtractor. So I'll come back in here, I'll say design compile all. I'll come back to my simulation restart and start stepping through. And you can make this bigger. You can do 1,000 nanoseconds per click. And so what have we got? We've got, 0, 1, 2, 3 minus 0 is just 0, 1, 2, 3. 0, 1, 2, 3 minus 1 is 7, 0, 1, 2. Well, why is 0 minus 1 equal to 7? What's up with that? Any ideas?
There has to be a sign of it, right?
Maybe.
So that means that like the. Oh, I guess that's wrong.
No, you're on the right track.
Well,
Yeah, it's 2's complement.
It's 2's complement.
it's like the biggest negative number you can have is 2 to the n. Like you don't and then the biggest positive number would be 2 to the n minus 1.
Yeah, yeah. So sum is 3 bits, right? So 3-bit, and we're using 2's complement. And so if I want to write the number -1, what do? I write the number +1. I toggle all the bits, and then I add 1. That's what -1 looks like in 3-bit 2's complement. Looks like the number 7. And sure enough, each of those 3 bits is equal to a 1. So 0 minus 1 is actually -7. 1 minus 1 is 0, right? Over here, 0 minus 2 is equal to 6. Well, why is it 6? 0 minus 2 is -2, which is +2 with all the bits complemented, with 1 more added. That's how we represent -2 in 3-bit 2's complement. A 1 and a 1 and a 0. All right, that's Verilog. It's building circuitry for us that does all of this stuff by just saying, take A and subtract B, and make the sum 2 bits. If I made the sum, make the sum 3 bits. If I made the sum 4 bits, I can compile that, I can reset, I can run my simulation. And now when I did 0 minus 2, or let's go 0 minus 1, what did I get? I got F, 1, 1, 1, 1. Why did I get F? Because in 4-bit 2's complement, -1 looks like this. And that's the hex value F. But if I don't like that, I could right-click on here, and I could come down to Properties, and I could say, let's look at this in decimal. So now I can see this was equal to 15. And if I don't like that, I can right-click and go to Properties, and I can say, Notation, signed 2's complement. Hey, there's my -1, there's my -2, there's my 0 minus 3 is -3.
Where did you go to notation?
So right-click on the signal you're interested in, come down to Properties, and then if you go to Value Format, you got all these options you can play with.
Oh, okay, got it. I see now.
So this tool works with everything that we've been doing, everything that we've talked about for the past 8 weeks, everything that you learned in 120, right? All that stuff helps you with this. And it's really set up to be, a pretty general purpose tool that that will let you develop and analyze and test your circuits pretty efficiently. Now we're still talking about structural Verilog here, but we're starting to move towards behavioral descriptions, right? We didn't say sum bracket 0 equals a bracket 0 XOR b bracket 0, sum bracket 1 equals etc., right? We just said, set my sum equal to a minus b. And so that's moving in this direction of like, here's what I want sum to mean. I want it to be the difference of these two things. And that's where we're going to move next week, is looking more at, instead of describing a circuit in the way we describe, take these gates and connect them together, we're going to describe higher level behaviors that we're after. But what I'd like to do is go a little off track here and show you a different tool chain for working with Verilog. And this is a tool chain that actually works with physical hardware, and just kind of give you an inside look into some of that. This is not something we're going to do in this course, right? For your labs and your homework, this is the tool you're going to use. This is the tool you want to understand. But I want to just take a look at a different tool chain, and see what that looks like. But any questions about this right now before we move on to something else? We'll come back to this next week for sure.
This is really cool.
Is it?
Check
It's
out Icarus.
Yeah, I mean, I think this is really fun, and it did take me a few tries to get into it, but once you get into it, it's such a world. And I can post some tutorials for Icarus, as long as people realize that's optional. It's not like something you're required to do for the course. All right, so let me see if I can make this work. Let's see. So this is software that's from Xilinx. Xilinx, I believe, is owned by Intel at this point, although Intel bought one of them and AMD bought the other, I think, and I'm never quite sure. But this is software that works with Xilinx FPGA. So this is a device called a Spartan, and let me just zoom in here. So this is an FPGA, and it's got, a ton of pins on the side. Most FPGAs use what's called a ball grid array, so you don't actually see pins outside, but underneath there's this two-dimensional matrix of little tiny solder bumps, and it gives you a huge number of connection points. This is an FPGA that has a few hundred connection points through these edges, but the bigger devices have thousands of points on the bottom. And it's got a model number that's hard to see, XC6XSLX9. That tells you what kind of part this is. And this is just a kind of breakout board. So that's the FPGA in the middle, and the pins that you can read from and write to are basically connected to these edge connectors. And there's a few switches here, and then there's some LEDs. And it drives through a USB port. And basically, you can use a tool chain like the aldec tool to design Verilog code, but then you can dump that code into this device, and this chip will actually, implement whatever code you designed. So I want to show you the beginning of that tool chain. We won't actually configure the hardware, but we'll see some interesting stuff anyway. So, and this is for a different board that I have. Well, let's get rid of all of this. So, you've seen that to do our design and compilation and simulation and setting up stimulators, there's a number of steps involved, right? If you want to actually take this thing and turn it into a physical piece of hardware, there's a whole lot more steps. It's a huge number of steps. And so with FPGAs and Verilog, we usually talk about a tool chain, right? It's a succession of tools that are run one after another. And, you know, from the command line, you would just type one command, which would do one piece of the process, and then type another command, and another, and another, another. And after, you know, 20 or so of these, you might end up with something that actually configures your chip. So the more modern versions of this look something like this, and this is really a front end to a whole bunch of tools that do the different pieces of developing your design. So here I have a circuit called an adder, and it looks just like the circuit that we developed in aldec. So two inputs, which are 2-bit numbers, and a sum, which is a 3-bit number. And then the assignment statement, sum equals a in plus b in. And there's also this thing called a user constraint file, which says these particular signals should be connected to certain pins on the physical device. And this was something I actually made for a different FPGA board, which is this one. And same thing, it's a Spartan device inside from Xilinx, but it's a different kind of device. But this is a fun little board. It's got some 7-segment displays, some push buttons, some slide buttons over here, plus a VGA port and an audio port, and a bunch of random connectors that we can use, and a micro SD card, or a mini SD card reader. So that's a fun little board. These things are cheap. This was like $30 at Amazon. And these used to be, you know, thousands of dollars to get this kind of capability. So the prices are definitely within reach. And this is the board we have a bunch of in the STEM building that, you know, when we're back in person, if you want to actually play with FPGAs, Izad or I can get you one of these on loan, and you can do what you want with it. So this was code that I wrote to work with that larger board, and these are just particular pins that are connected. For example, these sum bits over here, pins 46, 7, and 8, those are connected to these 3 LEDs. And, you know, you find a schematic for this, and you look at these LEDs and see which pins they're connected to, and that tells you how to make this constraint file. So, and then the inputs, I was coming from slide switches. And you can say, for example, this is going to use low voltage CMOS 3.3 volts. So logic 1 is 3.3 volts, logic 0 is 0 volts. And this says I want you to supply 12 milliamps of current. So you can specify a lot of details about this. We're going to mainly work with the Verilog. So here's my program. And I want to implement this. Okay, so there's a big green play button over here. If I click that, it will start doing a bunch of stuff. And let me make this more visible. Now this is a really simple module, right? It's one line of Verilog code, so it'll only take about a minute to build up. But, you know, larger designs, when I was doing this in graduate school, it was not uncommon to have a design that would take, you know, several hours, possibly a couple of days to compile, and end up with a design that you could push into your device. And that was where, you know, sometimes it would run for 36 hours, and then it would just say, you know, error detected, please try again. And, you know, you lost half your weekend for nothing. So what happened here? All of this stuff. So, you know, we created the Verilog code and so on. We created the user constraint file, and then it ran a step called synthesize. And synthesize is basically taking this and turning it down into what's called register transfer language. So it's really thinking of it as moving information from one piece of your system to another. And it goes through a series of steps for that. And then it tries to actually implement that on your physical device. So remember the fuse maps from programmable devices? You had to take your equations and decide, you know, this line is going to be this min term, this line will be that min term. I'm going to take those and feed them to an OR gate. Well, that's what the tool is doing for us, basically. And there's usually 3 steps: translation, mapping, and then place and route. And this is figuring out how to use the physical programmable resources of, say, an FPGA to implement your design. And this is usually where most of the time is spent. This is where you get into the multi-hours. And each of these is a series of steps. Mapping is using various genetic algorithms, machine learning kind of ideas, simulated annealing, all kinds of things like that. Place and route is looking at the resources that are actually available and figuring out how to use those. And if you go through this window, it shows you the results of each of these steps. So first it ran this command, synthesize XST, and it compiles your design. It does some analysis. Now, we didn't do any timing analysis, but it found a 2-bit adder with a carry out inside our design. That's what that plus sign generated. And it used a total of 1 2-bit adder with a carry out. And it tries to do some timing analysis. We didn't have any clocks or nothing like that. It knows the speed of the chip. Maximum combinational path delay, 6.697 nanoseconds. This is that timing analysis we talked about when we did state machines. What's the longest possible time it could take from when an input changes till the output changes? Well, it depends, It's not as easy as just adding up the delays of each piece of your circuit because you don't know which paths are actually possible. And you can ask it to do a very detailed timing analysis or a very crude one. So this was set for a pretty crude one, but it found, 6.7 nanoseconds, worst case delay. And then it starts trying to place this into our device. So this is the actual device. It's 144 pins. It's a speed grade of 5, which is a pretty slow device. And it took 2 seconds to do that, so that was pretty fast. And it used a total of 3 what are called lookup tables. These are truth tables. And there's a whole slew of lookup tables inside the device, 1,400 of them. It used 3 of them. And then there's another way this is divided into what are called slices. So 2 lookup tables per slice. So it used 2 slices out of 704. So about 1% of our device got used to make this adder. And then inputs and outputs, it used 7. Why? Because we've got 2 bits for A, 2 bits for B, 3 bits for some. That's 7 I/O lines. We have 108 I/O lines available. We use 7 of them, so 6%. Average fan out. So on average, the output of a gate can drive, multiple inputs. On average, each output is driving a little less than 2 inputs. And this is a measure that will affect the speed, the reliability, the power consumption, and so on and so forth. We don't care about most of this information. But if you're making a very aggressive design that has to run under very specific situations, right, all this stuff becomes important. Initializing temperature to 85 Celsius. Why? Because the timing characteristics change with temperature. Initial voltage 1.14, should be between 1.14 and 1.26. So it's a low voltage device. So there's all this stuff. This is fun to look at, especially when it's taking hours to compile and you want something to do. But we're not going to worry about it too much. But let me show you the fun part of this. Let's go down under Tools and let's look at the schematic viewer and let's look at the RTL version of this circuit. Well, that's what our circuit looks like. It's 2 2-bit numbers coming in and a 3-bit number coming out. And if I double click on this, I get a slightly more interesting picture, but not terribly. But there is an add module somewhere which takes these 2 inputs and this output, and there's a carry coming out, and those things combine to generate the sum. All right.
Were you good to see that RTL?
So I did that under Tools, and then Schematic Viewer, and I did RTL. But that's not the really fun one. Here's the really fun one, is when we look at the technology files. So click on Technology, same top level view, there's our adder. Let's double click on that, and what do we see now? Now we see something more like a schematic diagram. This is a circuit diagram. And these lookup tables, it doesn't actually use AND gates and OR gates, it uses these lookup tables. Well, these are like multiplexers that have been configured to generate outputs in response to certain combinations of inputs. This is a 2-input lookup table. Here's our first input. It goes through a buffer that just provides more current, and it feeds this input, and we can click on lines to highlight. It feeds all 3 inputs. That's the least significant bit. The most significant bit goes through a buffer, and that feeds these lookup tables, and the output of those go into buffers which drive our output. So we can go into one of these lookup tables, we can double click on it, and there's what it looks like. That's the schematic diagram equivalent of what this thing is performing. And we can look at its truth table. There's the 4 inputs. That's what the output should be. And we can look at the K-map that corresponds with. And the system analyzed the K-map, came up with equations. There's the minimized equations. I don't think those are minimized. Maybe they are. So this tool is doing all the stuff that we do when we design a circuit, but it's doing it for us. But you can go in and you can look at this. So I think green is 1 and red is 0. And so that's, you know, a good old XOR. We got the checkerboard pattern going. If you look at the truth table, 0, 1, 1, 0, what's the equation? You know, I0 bar I1 or I0 I1 bar. And there's the implementation. So depending on what tool chain you're using, which really depends on what your physical device is, it's a different set of specifics, but it's the same general flow. You enter in your circuit either as a schematic or as Verilog code. You usually specify some kind of mapping to input-output ports. You run your tool chain by usually hitting a big play button. It goes through different steps, and it in the end figures out how to place your device on the physical component. And then the last step, generate the programming file. This actually creates the stream of 1s and 0s. And then you run another piece of software and you take your device, you hook it up to your computer, usually through a USB port, and it will load the 1s and 0s into the board. And there you go, you've got a programmed device. So that's more complex than the aldec tool, but that's just kind of like a view of something closer to what you'd probably be using if you were doing this in industry or if you were trying to actually, you know, implement something in hardware. And like I say, when we're back in person, if you want to play with this, right, we have boards available. You can use, this is free software. It's licensed, but the license is free. But it's a bit of a challenge to get this working, as in, you know, it might take several days and emails and trying different things to make it work. It makes aldec look like a walk in the park, but once you get it working, it's fantastic software. The Altera tool chain, totally different but same idea. Seems to work a little easier. The licensing is a little less painful. But, you know, you get it dialed in once, and the more you do this, the better you get at figuring this out. So that's kind of a high-level view from start to end. So what I want to do next week is dig deeper into Verilog and look at circuits that involve clocks. And this is really where we're going to look at behavioral descriptions of circuits instead of describing, you know, gates and flip-flops and things like that. We're going to stick with, you know, here's what I want to have happen. When a clock ticks, if this signal is 1, I want this other signal to change to a 0. And we're not going to do the state machine synthesis we're doing in Homeworks. We're going to describe, you know, what's the higher level go. So we're going to start with something closer to the state diagram and figure out how to go from that directly into Verilog. All right, so again, no class on Monday. You know, Clark is closed on Monday. It's a holiday. I don't have office hours Monday. But have a good weekend, good rest of the week, and I will see you Tuesday. Thanks. And thanks for putting up with all the funniness on the presentation.
One last quick question.
Yeah.
Would you be okay if before class Tuesday I could demo my circuit, or if you can't, would it be okay if I recorded a little video of me demoing it?
Yeah, video will be fine, but there's always an hour of lab time before class, so you can just hop into the 250 room anytime after 11, and I'm always in there.
Okay. That'll be perfect, because I have intro to C 2 hours before that.
Okay. Yeah. Come by at 11 or anytime between 11 and 12, and I'll be there Tuesday, Wednesday, Thursday.
Perfect.
All right, cool. Have a good one.
See ya.
Yeah, that was perfect. Thank you very much.
All right, bye.